Hello, am I audible? Hello, am I audible? Can you hear me? Hello, am I audible? Size 1000, can you please tell me, am I audible? Please tell, am I audible? Okay, so it's 7 p.m. now. Okay, so first let me introduce myself. Hi, this is Shaurik. Right now I'm doing my research at Madras on electoral discussion. In every week on Saturday from 7 to 9, I will take a live session for the quantity topology 2 course in semester. Okay. Um, yeah. Uh, yeah. Can you please confirm me whether am I audible?
Yes, sir.
Okay. And can you see the screen?
Yes, sir.
Okay. Thank you. So the main purpose of this live session is to solve some problems and clearing doubt of yours. Okay. So if you at any moment of time in any particular theorem or some problem or issue, you without any hesitation kindly ask me, because this session is only for solving and clearing doubts. Okay, this session. So that's all. And one more thing is that you can see in the Google chat, I have shared a Google form link. Okay, so kindly mark your attendance by submitting the Google form. Okay, yeah. Let me share it again. Kindly mark your attendance by sharing the Google form. Okay, so people are joining till now, so I think it's better to wait for some minutes. So okay, so not yet. So for those who have joined just now, just look at the Google chat. There is a Google form share, so you can submit your attendance by you can mark your attendance by submitting the Google form. Okay, so kindly mark your attendance. Okay, so before starting, I want to know how many of you are from math background and how many. I mean, so just I want to know how many of you are from math background. Kindly raise your hands. Okay, or better, how many of you are from other background? Kindly raise your hand. feel not clear. Mm, just hold a second. Now is my audio clear? Now is my audio clear? Okay, thank you. Okay, so my question was that I want to know how many of you are from different background other than maths. You can just raise your hand. In maths. What about others?
Sir, I have done MSc in maths and I am currently pursuing PhD in mathematics, first year.
Which area?
Sir, it's the operator theory. I have not started my research work yet.
Yes.
It's just I've just joined.
Okay, okay, I understand. Good. And is there anybody who is from other background? Is there anybody who is from other background? Okay, so far everybody is from maths. No, that's good to hear actually. Okay. So before starting, let me tell that I've shared a Google form link for the attendance in the Google chat. Kindly mark your attendance by submitting the Google form. Okay. Okay. So coming back to the main business, that yeah. Okay. So first, okay. So I have seen that sir has started from the mainly compactness and most importantly, sir has started from the contraction principle. Okay. Okay, so first let me know how many of you are comfortable with the contraction mapping theorem, or if you have any doubt, please let me know. Also, if you ask me to explain that thing, or if you ask me to solve some problems, I'm also fine to do that. But please let me know what you want. Okay.
Sir, actually, I don't know contraction mapping, and actually, the basic for this topic is not clear for me. So, if you can start a little bit, then it will be very helpful for me.
Yes. Sure.
Thank
And
you, sir.
yeah. And what about others? What about others? Okay. So. Uh, You have said some sound is disturbing audio. Can you please tell? I mean, what some sounds being Mr. Fida? Yeah. Can you please what some sounds might be repetitive actually? Okay, okay. Since some of you, I don't know actually who, but told that you have some issues. You don't have a contract service. Okay, I will do that. Okay, but before that, I want to know whether all of you are comfortable with the compactness, because the contraction mapping theorem somehow uses the concept of compactness. Okay. Oh, fans sound. Okay. Okay, just hold on. I will be back within 5 to 10 seconds. Okay, so now is the sound. Now is there any disturbance on the sound?
No, sir.
Okay. So you have said compactness is okay. I mean, okay means you are fine. You are. I mean, you know the basics of compactness, right?
Yes.
Okay. 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 So okay. So let's start with the contraction mapping theorem. In between, if anybody has any issue or any doubt, please uh, stop me and ask. Okay. Don't ask in Google Chat. Unmute yourself and then ask, because I am writing this on the screen, so I could not see right now the what is going on the Google Chat. Okay. So unmute yourself and ask if you have any issue. Okay. So mm, yeah. So the contraction mapping theorem tells that. So the contraction mapping theorem is the following. Suppose we have some complete metric space. The completeness is important. Okay, we have some complete metric space, and suppose T be any given continuous map, it satisfies the following property, that distance between the point Tx and Ty is less than or equal to sum C times of distance between x and y for some for all xy and for sum c belongs to 0 and 1. Okay. Then this theorem tells that we will get a unique x such that Px equal to x. This is the theorem. I mean, this is the contraction mapping theorem. Okay. In the statement, any in the statement any confusion, any doubt in the statement itself.
No, sir, it's clear.
Okay. So this is a contraction mapping theorem. Okay. Uh, okay. So this statement. So do I need to go to the proof, or should I start with some theorems, or should I start some problems, or do I need to go to the proof? I mean, what do you
Sir,
want?
sir, it's better to go with some theorems.
No, no. I mean, contraction mapping theorem is a theorem. Now
No,
I'm
no,
asking you
sir,
whether
related to this.
solve some problems. Okay.
Okay, sir.
Yeah. Okay. So uh, first observe something, that in the statement of the contraction mapping theorem, we must have some C. I mean, if this C is there, then we will get some unique fixed point. Okay. This, I mean, existence of such a C is important. Okay. So one may ask that if we don't have some this type of C, then what about the fixed point thing? Okay. So it may have fixed point, may not have a fixed point depending on the situation. So for this, consider the following counter examples. Okay. So first, consider, define a function f r to r, x goes to x plus 5 by 2 minus tan inverse x. First, observe that does f have fixed point? I mean, this is a question. Plus try to do this. Now, one second. First, solve this two. Uh, yeah, first solve these two, then the counter example will come. Okay. First solve this. Take your time. So, can anybody tell me, does f has fixed point or not?
No, sir, it does not have any fixed.
Okay, good. What about others? And okay, and what about the second one? Ida, have you solved the second one? Okay, network. Okay, Fida, you can write in on the chat that have you solved the second one or not. Okay. Anybody has done the second one? I'm searching for some other problems. Okay, Sunday, yeah. So from basics, I mean, from which, I mean, from where should I start, please? I mean, you have idea of metric spaces, right? Okay, you don't know how to solve. Okay, okay. I will solve, no issue. What about others? What about the for the second one? I will solve it.
Sir, I am unable to do second.
Sorry, can you please repeat that again?
Sir, I tried second one, but I'm not getting anything.
Okay, okay, sure. Okay, sure. Okay, so let me solve. Okay, one second, I'm searching one thing. One second. Let me find some more questions. Okay. So for the fixed point thing, suppose, okay, by the way, I have just realized, so does everybody know the meaning of fixed point? Okay, by fixed, I mean, fixed point means some point x such that fx equal to x. This is what we mean by fixed point. First question asks to show that if any fixed point is possible or not. Okay. So let's assume fx equal to x. So, I mean, suppose if it is fixed point, okay. So let's assume fx equal to for some x naught, okay. So this is plus what? X naught plus pi by 2 minus tan inverse x naught is equal to x naught. This implies what? This implies tan inverse x naught is equal to pi by 2, right? But this is not possible, right? So, so f has no fixed point. Everyone understand the solution? Does everyone understand the solution? So the what was the second one? So the okay. So here we need to use the mean value theorem. For the second one, we will use mean value theorem. So how to do that? So I mean, so anyway, fx minus fy by x minus 1 is equal to some f dash psi, okay, for some psi. Now fx is given as x plus pi by 2 minus tan inverse x, right? So what is f dash x? F dash x equal to 1 minus 1 by 1 by x square. So anyway, this is nothing but x square by 1 plus x square, right? So observe this. So this implies what? So observe this implies mod f dash x is less than equal to 1. Correct? I mean mod f dash x equal to x square by 1 plus x square, and it is anyway less than equal to 1, right? So this implies that fx minus fy by x minus y, its modulus is less than equal to 1. This implies fx minus fy less than equal to mod of x minus y. Right? Okay. So in this way we can solve the second one. The main technical tool we have used here is the mean value theorem. So yeah, so that's all for the second problem. So now let me know, is there any doubt with the second problem? Okay, is there any doubt for any confusion for the second problem solution?
Yes, sir, clear.
Yes, yes. Yes, sir. Okay, so in which portion you have the doubt, or in which line? You can write in chat. I am looking at the chat also.
It's clear, sir.
And what about others?
So what I have done is instead of taking f of x as I mean by you have applied mean value theorem, no? So
Yes, yes.
I took just tan inverse only. I didn't take the whole x plus pi by 2 minus tan inverse. I took just tan inverse actually.
No, no. I mean, you are applying the mean value theorem, right?
Yeah.
In
And instead of taking a right side, you have taken f of x equal to x plus pi by 2 minus tan inverse x and then found out f dash and all. So what I have done is I didn't take the whole thing, I took just tan inverse. And the thing is, ultimately, I got it as 2 times mode.
sorry, I didn't get you. First, I don't understand the function fx is already given, right? So why you only took the tan inverse?
Uh, Sir, the thing is, I wrote modulus of f of x minus f of y, and in that we pi by two will get cancelled, and then I got a mode x minus y minus tan inverse x plus tan inverse y. So I just took tan inverse and I tried.
No, no. Firstly, no, no. The thing is, I mean, so what you have done is that x minus tan inverse x minus y plus tan inverse y, and you have written down in this
Yeah,
form x minus y minus tan inverse x, sorry, plus minus tan inverse y. You have written in this way, right?
yeah, yeah.
But the thing is that it is not always equality. It is less than equal to, because we have a very popular formula that mod of a plus b less than equal to mod a plus mod b, right?
Yeah, sir. I took less than or equal to. I didn't take equality.
Okay, okay,
I took less than or equal to. And I got it as 2 times mod x minus y.
got it. How you got the two times?
Uh,
I mean, because mod of tan inverse x, its derivative is 1 by 1 plus square, right?
yeah, its
So,
mode is less than or equal to 1.
sorry, 1, you are right, correct. Okay, you are right. But the thing is
And
that, yes, you are right. I mean, your way is right. But the problem is, this problem can't be solved in that direction, actually. Okay. You have to use Mendel theorem directly.
mm,
Your way is correct, but this problem cannot be solved with that way, actually. Okay.
yeah, I know that, yeah. Because I'm getting it up at last step, I'm getting it as 2 times less than or equal to 2 times mod x minus y. I didn't get just mod x minus y. I got 2 times. That's okay, sir. I just said that's what, like, what I did.
Your
That's
way
it.
is right, actually. But there is some. I need to observe something. That's why the two times mod x minus y is not necessary. So one is important. That's the point. Okay. Yeah. Okay. So okay. So in this for the second part, you have seen that mod of fx minus fy less than equal to mod x minus y, right? But one thing observed in the contraction mapping theorem is that uh, in the statement here we only have some small c, though c lies between 1, but but the distance of px and py is less than equal to some c time of distance minus 1. Okay, and observe that c belongs to open 0 1, so c can't be equal to 1. Okay, but the given function satisfied mod x minus equal less than equal to mod x minus c, and so from this maybe we can intuitively guess that this I mean, at least intuitively we can see that fx minus fy less than equal to c into mod x minus y. This type of thing not possible intuitively. Okay, I mean, some of you may get an intuitivity that this is not less than equal to c times. It is not possible. Okay, so that's why, I mean, if we can show by rigorously that mod fx minus fy less than equal to c mod x minus y, such a thing is not possible, then since it does not have a fixed point, so this thing does not contradict that contraction mapping theorem. Do you get my point? The thing is, in the contraction mapping theorem, we have some condition, that is distance of the distance of two images less than equal to some three times of distance of that 2 points. Okay, but the thing is, this contraction mapping theorem is not true if that condition is omitted. So for this, we consider this following example: fx equal to x plus 5 by 2 minus 20 plus 6. And then if somehow we can show that mod fx minus fy less than equal to c mod x minus y, then it must, then, I mean, the point is that since this function f has no fixed point and since R is complete, so this function cannot be written as mod fx minus fy less than equal to mod c into x minus y. Okay, so do you understand point? Please let me know.
Sir, will you please return to the definition of contradiction mapping?
Yes, yes. Oh, so you are asking for this theorem, right? Can you please repeat? So the theorem tells that possibly there is a network issue, so that's why it's anyway. So contraction of the theorem tells that suppose x and xd is a metric space which is complete. Okay, and suppose t x to x any continuous function such that distance between the point x and t y is less than or equal to 3 into dx minus y for some lies between open 0 and 1. Then we we will have some x inside capital X as a dx equal to x. Okay, so this is a contraction mapping theorem. Now observe that in the contraction mapping theorem there are two conditions. One is completeness and another is this dtx comma ty less than equal to c dx comma y. Okay, this condition has to be satisfied, then we can conclude some unique fixed point. But the thing is, in the following example, x goes to x plus 5 by 2 1 tan inverse x. In this example, we saw that x doesn't have fixed point, and then finally we saw that mod fx minus fy less than equal to c into mod x minus y. Sorry, c into mod x minus y. But this cannot be written of the form mod x minus fy less than equal to c into mod x minus y, because if this is true, then f must have a fixed point. So, I mean, this is one counterexample of the following fact that in the contraction mapping theorem, we should have this condition mod fx mod of, I mean, distance between tx dy less than equal to c into distance between x and y. So that's what I want to say. Okay, so any confusion, any doubt in these portions? Take your time, let me know. Okay, so I have everything is clear for this portion. So, okay, so now consider the following problem. So, yeah, so let X the compact matrix space and yeah, unique address function such that so this is a problem. I mean, you can't think as a theorem, but anyway, this statement says that suppose the compact matrix. Okay, so observe one thing that in the contraction mapping theorem, the condition on the matrix space was it's a compact matrix space, right? Or, yeah, it's a complete matrix space. Okay, but in this problem, we are given that the matrix space is compact. And if is any contour function such that distance is strictly less than for all x not equal to y, then show that f is unique fixed point. Okay. So so first try to show the uniqueness. I mean by assuming the existence of fixed point, try to show the uniqueness at least. Try to show uniqueness of the fixed point. Anybody please uh, tell if you are able to show the uniqueness of the fixed point. Anybody please? Any idea how to show the uniqueness of fixed point? I mean, you can start in the following way. Suppose f has two fixed points, that is, if x1 is equal to x1 and if x2 is equal to x2. Now, using the given inequality, try to show that x1 has to be equal to x2.
So this will not happen because uh, fixed point will be unique.
Hmm.
Because if we will take x1 and x2 as two fixed point, then d of f of x1 and f of x2 means the distance between f of x1 and f of x2 will be same as distance between x1 and x2, which will contradict our assumption.
Right, correct, very good. Yes. So yeah, so fixed point is zero. So what about others? Does others understand solution?
Same answer, sir. What the other person has said.
Okay, understood. Okay. Okay. So let's see how to check the uniqueness. So how to check the existence of fixed point? Let's see. Okay. So uh, so first claim is um, okay. So define a function capital F from x to r as follows: x goes to d of x comma fx. Okay, f is continuous. So f is continuous. Okay. Now, since x is compact, so infimum has been attained, right? Oh, oh no. Well, sorry. Yeah. Since x is compact, so infimum of f has been attained. So let infimum of f is equal to f of x naught. Okay. That is the x naught x naught. So at the point of view, this is equal. Now claim is the point at which the infimum has been attained, the value of the function has to be 0. This is the claim. That is, so this is our claim, that the point at which the infimum has been attained, there the distance, here the function capital F will be 0. And if that infimum is 0, then that point x naught will be what? Will be the fixed point, right? So, so how to prove the claim? So suppose this distance is strictly greater than 0. Okay. Now the given condition says that it's strictly greater than d of f x naught, comma f square x naught, right? So this implies what? We have seen the point, the infimum has been attained by the x naught, but the function is taking a value in strictly smaller than the infimum, right? So such a thing is not possible, right? You understand the point? You understand the point? The thing is, for our claim is that infimum is equal to 0. Okay. So if we can show that the infimum is 0, then d of x naught from f x naught equal to 0, right? This means what? X naught equal to f x naught, and this tells the existence of fixed point, right? So assume that infimum is greater than 0. Now the given condition tells that d x naught comma f x naught is greater than d f x naught comma f for x naught. So at the point fx naught, at the point of small fx naught, the value of capital F attains is, I mean, the value of capital F is strictly less than its infimum, but it is not possible, right? So the infimum, I mean, so the value of F at the point x naught has to be 0, right? And this implies x naught is equal to fx naught. So this shows the existence of fixed point. Understand? Anybody with confusions or any doubts?
Sir,
Yes.
sir, will you please explain once again that how d of x0 comma f of x naught is greater than d of f of x comma x square x naught?
Yes, sure. So look at the question. Here the given condition is that d of fx comma fy is true to less than d of x comma y, right? This is the given condition. Okay. So in the solution, d of x naught comma fx naught is greater than d of f of x naught comma f square x naught. Basically, we have applied small f on the both side, both of x naught and fx naught. I mean, this directly comes from the given condition. Understand?
Yes, sir. Clear.
Oh. And what about the, yeah, okay. What about others? Any confusion or doubts? Okay, so I think that it's clear to everyone. So, okay, so this question is one more part. So, uh, okay, I shall be back after 2 minutes. Okay, am I audible? Am I audible?
Yes, sir.
Okay. So yeah, the question I was to add here that what happen if x not compact? So this is the another part of the question. I mean, so okay. So observe one thing that in the previous question, the compactness has been used in the following fact. Since X is compact, that's why infimum has to be written, right? So now the question is that what will happen if the X is not compact? Okay. So this is the question. Think about it. I mean, so you need, so I mean, of course, intuitively you can guess it's a possible. So provide a counter example, that is you need to provide a function a which satisfies that given condition, but it has no fixed point, right? So yeah, so give some example. Think about it. So try to construct a simple function. So choose some non-compact space. Okay.
But if we will take x is equals to open interval 0, comma 1, and
Okay. X equal
f
to,
of x is equals to x by 2,
okay. Then
then this has no fixed point in that interval.
yeah, correct. Right. Very good. So she did the contracts level. Okay. Mm, this is one problem. Okay, one second. Let me think. So okay. So since you know the compactness, okay. So can you please confirm that whether you know the different criteria of compactness? I mean, what are the criteria of compactness? Can anybody please tell?
Let's say we know only basics.
Yes, yes. Whatever you know, please tell. I mean, what are the criteria of compactness?
Like
Whatever you know,
if
please tell.
we will say space is compact, a metric space is a compact metric space. If we will take any open cover of that metric space, and if that open cover has a finite subcover which covers that space, then we will say that the X is compact.
Yes. Apart from this, you have done any other definitions or another
Yes,
given?
there are sequence in metric space. There are sequential criterion for compactness, then limit point compactness.
Yes, yes, yes. Okay, good. Yeah, that's what I want to know. And what about others? Do you people know about sequential compactness and all?
Yes, sir. The same thing what my friend have said.
Okay, okay, sure. So, so consider this following problem.
So sets and all. Then finite intersection property.
Yes, yes,
Yeah, a few results are there regarding that.
yes, yes. I understand. Okay.
Then basic open cover, sub basic, and all those things.
Okay. So let X be a compact metric space, and let F X to X be any continuous function, such that d of fx comma fy is equal to d of x comma y. So that f is such. Here we have the inequality, sorry, here we have the equality here. And if this condition satisfied, then f has to be surjective. This is the question. Okay. And just as a hint, okay. So the main hint is that you have to here use the sequential criteria of compactness. Okay. Somehow you need to come up with some sequence, and then you need to somehow use the sequential criteria. Okay. So please try first. Okay. If anybody gets some idea or some way, please let me know. Okay, so okay, so let's see how to solve this question. So, suppose not. So let pick some p outside f of x. Okay, and obviously this f of x is compact as x is. Okay. Now Distance, consider distance with the point P and Fx. Now, since Fx is compact, so this distance, Fx is set here, okay? So this distance at the infimum is anyway, uh,
Sir, this must always be positive.
sorry, I didn't get you. Can you please repeat?
Sir, this distance should be positive, I think.
Yes, yes. This distance, the definition of this distance is, this is the definition of it. So this is the distance between a point and a set capital A is the defined as the infimum of dAx, where A varies over A, okay? So suppose this is A and this is the X, so by distance remain this thing, okay? So that's what by means the distance. And you must have seen, have you seen this thing before?
Yes, sir.
Okay, okay. So you know that if the set A is compact, then the distance will be attained at some point, right? Yeah, okay. Uh, so suppose P is some point out. Suppose if if possible, we take up P outside the set capital Fx. Okay. Now, since it's the in distance is different the infimum, so this is anyway less than equal to d PFP, right? And given condition, this given condition implies that this thing equal to d of Fp comma F square P is equal to d of F square P comma F3P dot 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 equal to d of Fnp Fn plus 1P, right? Okay, dot dot dot. Now, since X compact, so the sequence Fnp must have some convergent subsequence, right? Now, the thing is that, so if Fnp is sub convergent, then we are done. But in case if Fnp is not convergent, we can choose its subsequence, okay? But in case if we choose its subsequence, that subsequence will follow the same pattern. So without loss of generality, let Fnp convergent, right? So this implies what? This implies distance between any two consecutive terms of Fnp goes to 0 as n tending to infinity. Okay. Now we already, this this thing gives the following d of p comma fx. This is less than equal to d of fnp fn plus 1. And this thing goes to 0 as n tends to infinity, right? So this implies what? This implies d of pfx is equal to 0. This implies p belongs to f of x. You understand the solution? Because here we have used some lots of things. So please let me know, take your time, and let me know if you have any issues or any doubts with the solution.
Sir, will you please show the last part of this theorem?
Can you see?
Yes, sir.
Okay.
Yes, sir, it's clear, sir.
Okay. Okay. So let's move on the next problem. So on the following problem, let f x to y has a unique fixed point. So f compose f. No, sorry, I have written out mistake. Okay. So the question is actually this. So the question is that the if x to y is a given continuous function such that f to the power n, that is its nth composition, I mean n-time composition, has a unique fixed point. You need to check that f has a unique fixed point. Okay. So try think about it. Take your time.
Sir, if we assume that f has more than one fixed point,
Yes.
say there are two fixed points x and y. Then
Hmm.
by composing, then f of x is equals to x
Hmm.
and f of y is equals to y. Then on composing f on f of x is equals to x, this equation n times, then we will get f of n is equals f to the power n is x, and as well as f n y is also y. So in this way x and y become two fixed points of f n.
Yes, right, correct. So you have told the uniqueness part. So what about the existence of fixed point? I mean, you have done the uniqueness part. Just look at the trick and do it in the reverse way. You get the existence of the fixed point. So the way you have shown the uniqueness of the fixed point, the same way, just use that technique in the reverse direction. You will get the existence. Just try to do.
Sir, is it if we will assume that f has no fixed point, then f of x will not equal to x for any x in capital X,
Uh,
and then we will keep on composing f on both sides.
wait, wait, wait. Can you please repeat?
Sir, I was telling that if uh, we will assume that f of x is not equal to x for
Yes.
all x
Mm.
belongs to capital X, and then we will repeat the composing f on both sides, and in this way we will see that if in x has no fixed point, if in x is not equal to x for all x.
No, no. But the thing is that when I mean, for 2 points A and B, A not equal to B may happen, but FA may be equal to FB, right? I mean, F is not given to be injective function, correct?
Oh yes, sir.
So this way will not work, right? So try in a different way. What about others? Okay, so the way out is follows. Since Fn has unique fixed point given, so that's why Fn x naught is equal to x naught for some x naught, right? Now compose F on the both sides, so Fn plus 1 x naught is equal to f of x naught, right? So this implies what? F to the power n of f of x naught is equal to f of x naught, right? So this gives what? F of x naught is also a fixed point of f to the power n. But it is given that f to the power n has unique fixed point. So this implies what? X naught equal to fx naught. Understand?
Yes, sir.
What about others? Any confusion or doubts?
Sir, x naught is equal to f of x naught in the
Yes, yes.
last. Sir, how is it?
Can you please be louder?
Sir, in the last dx f of x naught is
Can
equal
you
to
please be
f
louder? I
of
could not hear you at all.
hello. Hello, sir.
Yes, now it's fine.
Yes, sir. Sir, we are using in the last the contradiction of the uniqueness.
Okay.
So how?
Yes, yes. So we have so first given that fn has a unique fixed point, right? So f of n x naught is equal to x naught. Then we compose f on the both sides, and then we get this equation that f to the power n of f x naught equal to f x naught. Okay. So this implies what? This implies f of x naught is a fixed point of f to the power n. But we have started the fact that f but we have started the fact that x naught is a fixed point of fn. But the given but we are given that we are given that f to the power n has a unique fixed point. Okay, so x naught is our fixed point by assumption, and then we get that fx naught is an also fixed point. So that's why by uniqueness x naught equal to fx naught. Understand?
Yes, sir.
So all you know, I mean, so yeah, okay. So you are familiar with the financial property, I guess. Yes, right. So mm, uh, no, no, wait. Sorry, it's my mistake. So consider this following example first. So So given question is that X is a compact matrix and n is a collection of closed subspaces such that it's increasing. That is, n is contained inside n plus 1. Then we need to check that intersection n is non-empty. So the hint is that here you need to use the finite intersection property. So try to solve it. Okay. Okay, so Frida, you have written no in the Google chat. No with respect to what? Sorry for that. I've noticed that thing. So you have written no for what?
It was for my previous question, sir. I mean, for your previous question, sir. It is clear for me. In that sense, I meant no.
Okay, 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 okay. So yeah, so now solve this problem. Or the hint is that you need to use the final reduction property from O. Solve. I shall back after 2-3 minutes.
Sir, what it will be if we if we take a finite collection like I mean A1, A2, etc. AN. Sir, can you hear me, sir? Sir,
So anybody could solve it or any way out found? Anybody? Take A1 A and its intersection. Okay. Yeah, and it's empty and intersection of A1. Right. Yes. Yes, Fira. You have said it correctly. Good. Uh,
yeah, it is using the result that as it's compact if and only if every class of closed sets with finite intersection property has a non-empty intersection.
yes, right. Very good. Yes, so that's all this problem only. Okay, now consider this function. Okay, so go to the next question. Okay, so I'm not writing down the solution because yeah. Okay, so suppose f(x to x) be continuous and let x be constant. Show that there exists a subset of x such that so the function is continuous, the matrix is compact. We need to find some capital A some subset of x for which f of that subset is equal to that subset itself. Okay, so here also first need to use somehow you need to come up with some sequence. They need to use the sequential criteria. Okay, sorry, finite division property. So try to somehow solve it. First try, then I will give some hint.
Sir, here A can be any set and any subset of X.
Yes, yes. You need to show that there exists some subset. There is some subset for which this will hold. You need to find that subset first, right?
Sir, X is a quantity. Hello.
Okay. So let me give the hint actually. So take a1 is equal to f of x, a2 is equal to f of a1. Now, and so basically in this way, an plus 1 is equal to f of an. Okay. Now observe one thing that an plus 1 is equal to f of an is equal to f of an minus 1. Okay, so one thing is that a2 is equal to f of a1. Okay, and this is subset of f of x, and this is equal to a1. So a2 subset of a1. Similarly, you can show a3 subset of a2. Similarly, you can show that an plus 1 subset of an, right? So you will get this n of compact subspaces. Why compact? Because initially a1 is f of x compact, a1 compact, a2 is equal to f of a1 compact, a1 compact, that is a2 compact. So a1 is the collection of compact subspaces, thus that an plus 1 subset of an plus 1. So the intersection an non-empty firstly. Okay, now try to show, now try to find the existence of this. The thing is, this is intersection non-empty, so actually you can take this set as A. Now try to show that if A has to be equal to A. Okay, but before going to that direction, first go through the hint and let me know if there is any issue, any doubt with the hint itself. Okay, first go through the hint.
Sir,
Yes.
yes, sir. Here, following the finite intersection property, sir, here intersection of an over n will be non-empty. So
Yes.
we will take that set intersection of an as n is equals to a.
Yes.
Then this a will serve our purpose.
Yes. Okay, so you understood the hint, right?
Yes, sir.
Okay. So now show that f of a is equal to a. You told correctly, but now you need to prove that a is actually f of a is equal to a. Okay. Now try to show that. Okay. So let me run the solution. So 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 you know one thing, that f of a intersection b is subset of f of a intersection f of b, right? So anyway, this implies f of intersection an is subset of intersection f of an, right? And this is subset of intersection of an minus 1. So this gives f of a is a subset of a. So up to this is everybody understood, right?
Yes, sir.
Okay. So now the main trick comes to the converse part. Okay. So choose some y belongs to a. Okay. Now given condition implies that this is equal to intersection an, right? I mean you can write n plus 1. Okay. So this is equal to intersection f of an. Okay. So y belongs to f of an for all n, right? So let y is equal to f of xn for xn belongs to an. So f inverse y intersection an, it is a non-empty set for all n, right? Correct? I mean, since xn belongs to this, so that's why f inverse y intersection n is a non-empty set, right? Okay. Yeah. So f inverse y intersection non-empty, right? Yeah. So now the thing is that this intersection is also closed. I mean, it's a closed subset because the n is already compact, so closed, and f is continuous, so f inverse y is closed. So this is a closed subset, and also we have this relation, right? N plus 1 intersection f inverse y subset of n intersection f inverse y, right? So this implies what? By finitization property, intersection of an intersection f inverse y non-empty, right? So this implies what? This implies f inverse y intersection of intersection an non-empty. This is nothing but what? This is nothing but a. This implies what? There exists x belongs to a, such that f of x is equal to y. Okay. So this implies what? A y belongs to f of a. So we have started with some y in capital, and then finally somehow we come up with the solution that y belongs to f of a. So yeah, that's it. So go through the solution right now once again, and let me know if there is any confusion and doubt. In between we have used the finds and property again. So that's the main technique. Please go through the solution and let me know any confusion and doubts. Yeah, please go through it. Let me know if there is confusion at all. Okay, so I hope that everyone understands the solution. Okay. So the next, okay, so before going to the next problem, let me know whether do you have any knowledge of this thing C01? Do you know anything about this, or have you heard about this?
The set of all continuous function in the interval 0 1.
Good. And do you know that it is a complete metric space?
Yes, sir.
Okay, and what is the metric?
It's sup normal.
Yes, okay. So, okay, so solve the following problem. Okay, one second. Okay, sorry, let me write it down again. Square. Question is that k is a unit square on the k is a function of a unit square with mod k x y less than equal to 1. So that we will find a continuous function is satisfy the following condition. And the next question is um, I mean, is such a function is unique? Okay. The thing is, hint is that C01 is a complex matrix. Okay. So somehow you need to use the contraction mapping theorem. So try to solve it. Okay, so I think it's better to give the hint actually. So hint is define a map T from C01 to C01 by T of f of x equal to e to the power x square minus integration 0 to 1 kxy fy dy. Now show that P satisfies the following condition in the contraction mapping theorem. Okay. Now try to show this. I mean, if you can show that, then we are done, right? So try to show that F satisfies the condition. Anybody, please? Okay, let me write it down. So now T of f of x minus T of g of x. This is equal to integration 0 to 1 kxy fy minus gy dy, right? This is less than equal to integration 0 to 1 m mod gy minus my dy. Okay. Our aim is equal to supremum norm of capital of the function. So what? So this is less than equal to, and this is less than k due to the given condition. So this is less than equal to m into norm g minus f. So this implies what? Norm tf minus tg less than equal to norm of g minus f. This implies t has unique fixed point. So there is a unique f such that fx equal to e to the power x square minus integration 0 to 1 kxy fy dy. So this is the technique. I mean, this is the way out of solving this problem. Please go through solution. Let me know if there is any confusion or doubt, or if you have any doubt of the previous problems. Please let me know.
Sir, clear, sir.
Sorry, can you please repeat?
Sir, it's clear.
Okay. What about others? Others, anybody have any doubt, any issue, or confusion? Okay, so I think everybody understands. Okay. Okay. So So that's all for the fixed point. Okay, so on the next session, that is on upcoming Saturday, we shall start some new thing. Okay, so I mean, I can go with the how the sir goes accordingly. I can go, but since this session is only meant for um, clearing concepts and the solving some problems. So first, let me know whether the whether the problems that we have solved today, uh, is this type of problems are fine with you, or do you need some hard problems, or do you need some easy type of problems? First, let me know this. I mean, this type of problems are fine. I mean, this type of hardness of this problem, should I increase or should I decrease? First, let me know. Or first, do I need to start with some easy problem? Then gradually we should go with some hard ones. Anybody? Okay, sure. I'll not do this surely. And okay, so next day, okay. So next day I shall start with the according to search direction. Okay, but but if you have any issue and doubts, please let me know. Accordingly, we can start some new things. Okay. Or right now, if you can suggest the which topic I should go in the next session, then it will be better for me also. Please suggest if you have any particular topic. Okay, so no particular suggestion. Okay, so I'll start with the according search direction. Okay. Also, yeah, I got that in there. Yeah, I got that in this way. Okay, so that's all for today's session. Thank you everyone for attending the session. Okay, so I am stop. I'm going to stop this meeting. Okay, I'm yeah, disconnecting the call. Anybody in doubt or any issue before I disconnect? Please let me know.
No, sir, it's okay. Thank you, sir, for the class. It was very good, sir.
Okay,
It was
thank
very
you.
helpful. Thank you. Thank you.
Yeah, okay. Okay, so I'm leaving the call.
Thank you, sir.